This component of your course is titled Elements, Atoms and the Periodic Table. The periodic table is a system for categorizing elements based upon some particular key physical and chemical properties. Unknown at the time of its creation, what it represents is a map of the quantum nature of subatomic structure. This is truly one of the most important discoveries of our time, and is the basis of all chemistry. What I will do in today's lecture is take a historical perspective, looking back at how people used to think about matter, what it is and how it behaves. And in trying to answer these fundamental questions with scientific methods, we will discover much about the world in which we live. Now, let's begin at the beginning. Clearly, since people have been people, we've been acutely aware of different types of materials in the natural world. The creation of shelter, of clothing, the gathering and processing of food all require skills and tools that depend upon a really good understanding of the properties of many different natural materials. Here's an example. 8,000 years ago, if you wanted to cut something, you need a material that was hard and can be made sharp. Some rocks are much better at this than others. The sites where we find Neolithic axe-making activity coincide with the places where we find the most appropriate rocks. Here's a material with a particular physical property that's crafted and often exported, being used a great distance from its source. It's no surprise that Stone Age man knows a thing or two about stones. Okay, now most rocks are composite materials, being comprised of many different minerals. Occasionally, we find rocks where some minerals are concentrated, and it is here where people have first encountered pure elements. When I say pure elements, I want you to think about the meaning of the word purity. Actually, it's quite a good time for me to introduce a couple of really important concepts in chemistry that both relate to the concept of purity. So the first concept is that of homogeneity. Something is homogeneous if it is the same throughout from one side to the other. If this is not the case, we use the word heterogeneous, meaning different in different places. As I said, most rocks are made up of a number of different minerals. So in this piece of granite there is quartz, the clear crystals, feldspar, that's the white crystals, and there is biotite mica, that's the black crystals. If you are zooming in at the scale of these crystals, clearly these are three different things all mixed up in this rock. This is clearly a heterogeneous material. If we just had one crystal, say quartz, then it is uniform throughout and is a homogeneous material. If we just had a rock made up of one sort of mineral, such as this quartzite, which is made up of thousands and thousands of small crystals of quartz, then it is also uniform throughout, and it is also a homogeneous material. If I were to say which is more pure, granite or quartzite, you'd say quartzite. Certainly, heterogeneous materials are by definition mixtures, and so not pure. There's another thing I need to say about homogeneity. This rock is basalt. It looks pretty uniform. It looks to my eye to be homogeneous. But I can tell you it has the same composition as granite. It's just that the crystals are a lot smaller. Use a microscope and you can reveal the heterogeneous structure of this rock, so it's not a pure mineral. It's a mixture. The sense of whether something is homogeneous or heterogeneous often needs to be qualified with a length scale from our observation. So homogeneity is an indicator of purity, but it alone is not sufficient. You may have a mixture where the components are more intimately mixed. For example, seawater is clearly a homogeneous material, but it is definitely a mixture of water and salts. I said just now that most rocks are heterogeneous and thus impure, but sometimes we find rocks where some minerals are concentrated, and the rock may be a more pure thing. And occasionally, the minerals may be pure elements. Gold is a good example. Shiny, malleable, ductile, it has properties unlike anything else. And because it's also rare, it's highly prized and valuable. We know from many artifacts that ancient people were able to work and process this material. Where did it come from? Why is it this element that's been known since antiquity? These two questions are related. Where did it come from? Well, sometimes you just get lucky and find a lump of it. Gold, like silver and copper, exists on Earth in a native form, meaning as a pure element. Processes in the evolution of Earth have locally concentrated these elements. It means in some places you can just collect these elements as a mineral from amongst other rocks. For the second part, why is it that this element is known since antiquity? In fact, for these three elements, gold, silver and copper, is because of their chemical properties. These elements, and gold in particular, like to stick to themselves. What I mean is they are relatively inert and unreactive when compared with other elements, and in general they do not mix so well with other elements. Hence they occur as native minerals, and you don't need technical processing skills to get them, you just need to find them. In addition to the few elements that exist in a naturally pure form on Earth, there are also a handful of other elements that were known in antiquity which are really easily liberated from other materials. For example, mercury. Mercury is formed by the thermal decomposition of its ore, cinnabar. It's easy to imagine that this chemical process was first discovered by somebody throwing red rocks of cinnabar onto a fire, and in the morning, when the fire has died out, finding droplets of metallic liquid mercury in the hearth. Imagine yourself 4,000 years ago being the person who did this. You might reasonably think that you were some kind of great magician. Similarly, lead, tin and copper are all easily obtained by fire, by roasting their ores. This smelting is a chemical process, and being able to do this with tin and copper combined makes bronze, giving us a whole era of human history. Now remember that the Bronze Age is replaced by another elemental age, the Iron Age, although exactly when depends upon when this new technology reaches your part of the world. Iron is a very, very common component of minerals and rocks, but it is only readily extracted from ores like hematite, in which it is very concentrated, and here the extraction process is a little more difficult. Actually, with mercury, you can just really warm the cinnabar rock. With iron, you've got to heat it up to about 1,500 degrees centigrade in the presence of carbon, such as coal or charcoal, and you need to add some chalk or limestone. Let me emphasize that. You need to have the right combination of things in the right proportions, and you need to heat it up to unbelievably hot for quite a long time. With the more challenging processing needed to create iron, we now have many skilled individuals experimenting with materials and conditions. These people begin to look more and more like early scientists, or indeed early chemists. After iron, we have the discovery of the elemental materials zinc, arsenic, antimony and bismuth. We have found archaeological objects made from these elements, but exactly when, where and how these elements were discovered remains a mystery. At this stage of human history, we enter the age of alchemy, and I want to tell you about one man and the discovery of one element in particular. It is the element phosphorus, and it is the first element where we know precisely where and when and by whom it was discovered. The manner of its discovery tells us about an important time in the early history of science. Henning Brand was a German alchemist. The well-known ambitions of the alchemists were A. Gaining immortality, achieved by finding or making the philosopher's stone, and B. Becoming fabulously wealthy, by discovering the secret to turning lead into gold. And while the term alchemist and magician seem a bit interchangeable, many of the experiments performed by these men were studies of chemical reactions. These alchemists created and studied many chemical transformations, although they did not have adequate theory to explain what it was they were actually observing. So, in 1669, during his experiments on urine, sand and charcoal, Brand produced a white waxy solid, which on exposure to air shone with a brilliant white light. With his newfound recipe to make light from pee, Brand toured Europe showing off his discovery. The white waxy solid was a new material, which became known as phosphorus, meaning giver of light. Which brings us to Robert Boyle, a contemporary of Henning Brand, Boyle was an Anglo-Irish aristocrat who did have some understanding of what it was that Brand had discovered. Being wealthy, Boyle had the time and the money to allow him to pursue his interests, and amongst other things, Boyle was interested in alchemy and the nature of the things in the world. In thinking about matter, Boyle realised that amongst the many materials known to man, some were rather special, some were elemental. As Boyle saw it, the alchemists often combined things to make something new, and sometimes they took a thing and split it into two other things. Boyle realised that some materials did not seem to be able to be split into other things, no matter what you did. He said such materials were elemental, or elements, while other materials were made up from two or more of these elements. These compounded materials were what we now call compounds. This idea was published in a book called The Sceptical Chemist in 1661, and it remains the definition of element and compound that we use today. Boyle understood that Brand had probably discovered a new element. Boyle's revolutionary book marks the end of the magical alchemy and the beginning of the scientific subject of chemistry. So after phosphorus, gradual discovery of more and more elemental materials, each element having its own properties. I won't go through all the element discovery stories, but in 1735, Jules Brandt discovers cobalt from rocks known to German copper miners as goblin ore. This goblin ore was a real problem. It looked like it should contain copper, but when smelt it failed to produce any, so clearly it must have been cursed by goblins. The German word for goblin is kobold, which becomes cobalt. Then 1747, Don Antonio de Ulloa discovers native platinum. 1751, Axel Frederick Cronstedt discovers nickel. 1766, Cavendish discovers hydrogen. And 1772, Daniel Rutherford discovers nitrogen. And then 2 years later, Hardluck Scheel discovers chlorine. And that same year, Johann Gottlieb Gahn discovers manganese and Joseph Priestley discovers oxygen. You can see that there is a steady stream of new elements being discovered, but I need you to realise how difficult it is to prove that you have a new element. By definition, it is a material that cannot be broken down into other things. But just because you can't find a way to break it apart doesn't mean that such a way does not exist. It's a bit like unicorns. Just because you haven't seen one, that's not scientific proof that they don't exist. The other big problem at this point in history is that we don't really understand what matter is. We know elements are important, but we don't know why. Roll up the next significant character. French aristocrat, administrator and scientist Antoine Lavoisier. Lavoisier's careful experiments on matter allowed him to formulate some fundamental postulates about the nature of matter and mass. With these insights, he became known as the father of chemistry. Lavoisier's key discovery stems from his access to a new scientific instrument, a precision balance, so that when he studied any transformation, a chemical reaction, he found that the masses of consumed reagents and the mass of any product always had a constant ratio. If you added too much of A, then some A would be left over, often mixed in with the product. Too little of A, then it would mean you had too much of B, and you'd have some B left over. The implication of this observation means that different materials have different characteristic masses. That is, each element and each compound has a characteristic mass, and that there is some definite proportion in which these things combine or separate in a reaction. Moreover, Lavoisier realized that this mass associated with matter can neither be created nor destroyed, meaning that matter itself can neither be created nor destroyed. And so in all reactions, things are transformed, but the total mass at the beginning and the end is the same. This is an absolute truth. If you don't observe this behaviour, then you're missing some part of the transformation. There is some component you're just not seeing. Let me give you an example. Heat up 100 grams of limestone
to be red hot, and then cool it down, and you will always get 56 grams of lime. The lost mass here is 44 grams of carbon dioxide, an invisible gas not seen by observation. But change your reaction setup and you'll be able to capture it, just as Joseph Black did. So, Lavoisier's studies of matter and mass give us one of the first great conservation laws, the principle of conservation of mass. What is more, these simple facts about matter and mass have some profound implications for the nature of matter. In order to have some compound C made up from elements A and B, it must be some fixed, meaning not varying, mass-carrying unit of A and B that combined in a definite, meaning discrete, proportion. This leads us to the idea that there must be some minimal sized part of A and B that is fixed and cannot be arbitrarily broken down into other masses, which nicely brings us to the next individual in this story, John Dalton. Dalton is a teacher and a scientist based in Manchester. He expands the alchemical symbol representation of elements, giving new elements simple letter codes. Like others, he was listing elements along with their relative weights, relative to the lightest known element, hydrogen. Dalton used his system of element symbols as a way to depict compounds by combining symbols in particular stoichiometries. You can see here what we can recognise as nitrogen monoxide, dinitrogen oxide, nitrogen dioxide, the nitrate anion, and dinitrogen tetroxide. But the key idea that Dalton clearly tells us is that the only way that dots of elements have a characteristic mass is if there is some minimal subunit that is the essence of the element that cannot be further divided. Dalton gives us atomic theory, the theory that the world is made up of vast numbers of minuscule atoms, and each different type of atom corresponds to a different element. In this way, the fixed proportion of elements in a compound is obtained by counting the proportion of atoms. So the invisible gas discovered by Joseph Black contains twice as many oxygen atoms as carbon. We can see how its symbolic depiction has evolved. And so when we write a chemical formula for carbon dioxide, each occurrence of a letter corresponds to an atom of that element. The subscripts tell us the proportion, but by convention, when the subscript should be a 1, we don't bother to write it. At this point, we have a growing list of elements, each one made up of a different type of atom. And these atoms are the fundamental building blocks of all matter in the universe as we know it. But how can we organise them? How can we categorise these different types of elements? In their pure form, there is tremendous variety. Think of the pungent brown-orange liquid bromine, or yellow crystals of sulphur, invisible gas nitrogen, soft malleable grey lead, or the hard shiny crystals of chromium. But while there are huge differences between many elements, there are also families of elements that show great similarities. Lithium, potassium and sodium are soft grey metals, highly reactive, and their compounds are almost always white and soluble in water. And these salts show clear patterns in their stoichiometry. The next character in this story is Johann Wolfgang Dobereiner. Dobereiner noticed that there was a mathematical relationship between the characteristic masses of some groups of chemically similar elements. It appeared to him that the elements came in groups of a triad, which if you rank them in order of increasing mass, the mass of the middle element is the same as the mathematical mean of the outer two. It's also the case that the middle element had intermediate properties and behaviour. Dobereiner saw this for lithium, sodium and potassium, and also for chlorine, bromine and iodine, and for calcium, strontium and barium. The idea of triad families is clearly important, but it doesn't seem to work for all elements. About 30 years later, along comes John Newlands, and he proposes an alternative way to find patterns of behaviour in the growing list of elements. Newlands listed the elements in rank order of increasing mass: hydrogen, lithium, G is glossinium, which was later renamed beryllium. Newlands noticed that there were similarities in the behaviour of every eighth element, so he creates a table where elements are listed in columns of increasing mass, but when he gets to the eighth element, he starts a new column. Now elements with similar behaviour are in the same row. This correlation, where similar elements are in the same row, is really clear and strong at the beginning of the list, with, for example, lithium and sodium and potassium in the same row. However, the strength of similarity rapidly decreases as we progress through the sequence. In addition, Newlands made an unfortunate error in his presentation to the Royal Society. Newlands tried to make a connection between his element ordering theory, where every eighth element is similar, and musical theory, where every eighth note is an octave away. His idea of octaves of elements was widely rejected at the time. 4 years later, Russian Dmitry Mendeleev hits upon an ordering of elements that is much more successful in sorting out elements by their chemical behaviour. Here it is, Mendeleev's table from 1869. It's quite a lot like John Newland's ordering. It is transposed. Columns become rows and rows become columns. So Mendeleev has 8 columns which he calls groups 1 to 8. He fills in the elements moving along a row with increasing characteristic mass. And then he starts a new row after the 8th one is full. Mendeleev is using chemical properties like the stoichiometry of elements within compounds as a measure of similarity. You can see the composition of hydrides and oxides associated with each group. But in addition, Mendeleev was clearly very cautious in the way he created the table. You can see there are some question marks against elements he's not sure about. He's right to do this. Look at Di 138. That's didymium. We now know that this is not an element, but a very difficult to separate mixture of praseodymium and neodymium. He's also put some elements in brackets. See copper, silver and gold, which are all placed in group 1, and although the stoichiometry of many of their compounds fits, there are also very significant differences from these elements and the likes of rubidium and cesium. Notice how Mendeleev has staggered their position. He is aware of the limitations that his table brings. The other thing that Mendeleev did that made his table so successful in categorizing elements is that he did not blindly stick to the ordered list of elements in constructing his table. Instead, he left space in the table. If it made more sense chemically, he moved the next element to a more appropriate group. The gaps that Mendeleev made, where he'd skipped a space, are marked with a hyphen. So in this organisation, Dobereiner's triads are consecutive elements in a group. But now these families are no longer limited to 3 members. Mendeleev has also used the element mass relationships first spotted by Dobereiner to predict the masses of missing elements. What Mendeleev has produced was a map of elements categorized by chemical behavior, and in which he had predicted the existence of as yet undiscovered elements. He's also said what their mass should be, and most usefully from the position in the table, how they should behave, which gives others insight into where they might be found. It's no surprise that Mendeleev's table quickly led others to discover these missing elements. You'll notice that Mendeleev's table does not look exactly as the modern version of the table. The difference is that in the modern table, we've stretched things out a little bit. In creating a few more new columns, we avoid having situations like where silver and gold are in the same group as lithium, sodium and potassium, etc. So that was the historical basis for the periodic table. We need now to find out why it had the shape and structure that it does. This will take us into the realms of quantum mechanics and subatomic structure. But before we go there, I will in the next unit build on your basic knowledge of chemistry of the different elements by looking at the characteristic chemistry of elements in different parts of the periodic table. So until then, bye for now.